Share the screen. So how's it going with the homework? Good. There's not that many people here today, so hopefully that means homework is done. We're gonna move to find elements in 2D. I kind of mentioned this a little bit on Friday. Didn't really have too much time to get into the details, so we'll do a lot more of the details today for find elements in 2D. We will do, let's see, what do I have in this set of lectures? Let me add a little bit of sort of a recap of what I showed. A little bit of I mentioned this on the Python Lab 4, but the idea of the meshes in 2D is very similar to the 1D. There is going to be an array that is going to be this node X array, which is going to have the XY coordinates of every single node. The difference between this and the previous one is that before it was just single X coordinate, now there's going to be XY coordinates. So the size of this is going to be number of nodes, comma 2. And there's going to be also an elements array. And that one, depending on what elements you have, for example, triangles, then you will need 3 nodes. So for example, 0 to 3, that's basically if you have a triangle and then somehow this is node, let me draw more than one triangle. Let's say this is 0, 1, 2, 3 for the nodes, and this is element 1 and element 2. Okay, let's do it like that. Well, element 0, let me call it with so let's see, there are 4 nodes. So the node X would have 4 rows, and I'll just randomly give some coordinates. Let's say that node 0 has coordinates 0, 0. Node 1, let's say, has maybe 1, 1. Node 2 seems to have something like 0, 2. And node 3 seems to have something like minus 1, 1. And there's only 2 elements in this mesh. So element 0 is made out of nodes. And here it doesn't matter the order. Element 0 is made out of nodes 0, 1, and 3. And here it doesn't matter which way you write them as long as you do it counterclockwise. So you can either do 0, 1, 3, 3, 0, 1, 1, 3, 0. Either one of those works. As long as it's counterclockwise. These are the nodes that make up element 0. And then element 1, should rename it to element 1. Element 1 is made out of nodes. And this is, so it's node 0, node 1, node 2, node 3. This is element 0, element 1. Element 1 is made out of nodes 2, 3, and 1. And again, which order you want to do them, it doesn't matter as long as it's counterclockwise. So 1, 2, 3, 2, 3, 1, 3, 1, 2, all of those will be equivalent. I guess that is for the mesh. Now, given a mesh similar to before, we need shape functions. And before I scroll down, if there's 3 nodes for an element, there's going to be 3 shape functions. So for triangles, there's going to be n1, n2, and n3. And there's one thing that we will have to be careful with is similar to the 1D case, the shape functions can be in terms of xy, or we'll do another isoparametric map later on, but the initial one is to have functions directly in terms of xy. Directly in terms of xy. But later on, isoparametric map. Actually, this lecture just a little bit later. What do these shape functions look like? They have to be similar to the 1D case. They have to be continuous and complete. And we're not really going to go into details of how to guarantee that these shape functions are continuous and complete. But for them to be continuous, actually that one is easy, because for them to be continuous, all they have to do is be 1 at a particular node and 0 at the other nodes. And if we do that, then they will satisfy this interpolatory property, which makes them continuous. And so for that, I can scroll down. So this is, for example, for the triangles, these are the shape functions directly in terms of x and y. And they are such that they are 1 at a particular node and 0 at the other nodes. So shape function 1 is 1 at node 1, 0 at the other 2 nodes. Shape function 2 is 1 at node 2, 0 at the other 2. Shape function 3 is 1 at node 3 and 0 at the other 2. So this is very much the same as what we did in 1D, where they are 1 at a node and then go to 0 at the other node. These obviously look a lot more complicated than the 1D ones, but again, they are just functions of x and y. And then if you recall for the 1D case, for example, the first shape function was x minus x2 over x1 minus x2. So in that shape function, x1 and x2 were the coordinates of the element in 1D. For the triangle, you need x1, x2, and x3, and y, y2, and y3. So you need the xy coordinates of the three nodes. So that's why it looks a little bit messier. But the idea is more or less the same. At the end, it's a function of x and y, and you need to be parameterizing it with nodal coordinates. Any questions up to this point? All right, what do I have here? There we go. Okay, so we have a mesh, we have the shape functions. Why do we care about the shape functions? Because we want to interpolate any function using these shape functions. So this I kind of showed as well on Friday, but the structure is pretty much the same as in the 1D case. So if you want to interpolate a function, all you have to do is sum the shape functions evaluated at a particular xy times the nodal values. So if you are interpolating a temperature field, which is called theta, then you have the value of the temperature at the given nodes, theta 1, theta 2, theta 3. So then what is the interpolation? If I want to evaluate theta at a particular point, then all I have to do is evaluate the shape functions at that particular point and then multiply by the nodal values and sum. Very much the same as in 1D. What if I want the gradient of that value theta at that same point? Actually, I can do it. We can put some values into it so that I don't want to do that. Well, I'll do it and I'll open a Python notebook to do it. Maybe not. Well, if I have time, we'll do it on Python. But do. So let's say that we have, I won't evaluate the shape function because it's going to be difficult, but let's do 1, 0, and let's do 0.5, 0.5. Actually, this looks more like in the middle, something like that. Let's say these are the coordinates. And then let's say that theta at this value is 2, theta at this value, at this node is also 2, and let's say that theta at this node is 5. So what these two lines tell us is that if I want to know the value of theta at any point inside of that triangle, all I need to do is evaluate the shape function at that point. So let's pick a point. Let's say that I want to evaluate here at whatever x equals 0.1, y equals 0.1. Is that inside of the triangle? Let's do 0.2, 0.1. I think that would be inside of the triangle. 0.3, 0.1. I don't know if 0.1, 0.1 is inside of the triangle. It definitely has to be inside of the triangle. And so if I want to know the value of the temperature at that point, all I would do is evaluate that first shape function at that value, multiply by the value of theta 1, evaluate the second shape function at that same xy value, and multiply the theta 2 and evaluate the third shape function at that value, and multiply by theta 3. And that will give you whatever value of theta is at that location. I don't know here because I don't want to evaluate the shape functions, but more or less, what would the value be? Definitely somewhere between 2 and 5. Right, so it's going to be maybe, I don't know, 2.5 or something like that. It seems like it's only changing from the bottom to the top. And you could do that for basically a ton of points inside of the triangle. And what you would get is if you evaluate for many, many points, you would end up evaluating the corresponding contour. Right, so if you repeat this many, many times, and this is the same idea as what we did in 1D, is if you evaluate this a lot of times, you can get a plot. In 1D, we were evaluating for, I don't know, 50x values between the beginning of the element and the end of the element, and then we were getting the plot. Now a plot, because we are working in 2D, a plot is represented with a contour. So we would have a contour plot. Questions about that? Yes. In this case, I'm just giving them, I'm just assigning them. I mean, when we do the solution of the problem, that's actually what we are trying to solve for. But this is, if you have some thetas, the shape functions allow you to interpolate the theta at any point inside of the triangle. For the gradient, the idea is the same as in 1D. So if you have the thetas and you want the gradient, all you need is the gradient of the shape functions times the nodal values. In this case, what does the gradient would look like? Well, it will likely be something pointing up. This is likely the gradient of theta evaluated as 0.3, 0.1. is going to point in the direction of the steepest ascent. So in this case, I would expect it to point basically up. But again, the same idea. We have only the shape functions are functions. The other things are nodal values. So if you want the gradient of theta, all you need is to know the gradient of the shape functions and then just multiply by the nodal values. Any questions? This is more or less what I was doing on Friday, and I can go back to it later on. I can go back to the Python, but I'll move first to change. Now we'll do the isoparametric map. So we're gonna switch gears a little bit. In many cases, I mean, these shape functions in terms of xy, it really only works for the triangles. But then once you have, for example, quadrilaterals, impossible to get shape functions directly in terms of xy. So we will have to do the isoparametric map. So before I show it here, I see it here. Let me put one extra page here, just to give you a little bit of an idea of what we're gonna do. But the main idea is, let's say we have the XY space, right? And we have our object, and we have triangles here in XY space. Let me zoom in. So we have some triangle in XY space. And the problem is that it's very difficult to do integrals in XY space. It's very difficult to define the shape functions in XY space. So what we are going to do is we're going to map that triangle to another space, which you can already imagine. It will have this psi, and then we need two variables because it's 2D, psi and eta, and then we somehow need to decide on some parent triangle. In this case, it's going to be this triangle, which is going to have coordinates 0, 0, 1, 0, and then 0, 1. Let me move this to the side so that I can show the analog to the. So in 1D, we had, similarly, I had some X and I have an element here. And then we had the Xi, and here we always had the -1 to 1. And then we wanted to build that map. It's the same thing here. And it will also generalize when we do quadrilaterals. Then we will have also a quadrilateral in XY space, and then we'll somehow define a psi eta quadrilateral. So this is, I think I want to skip the next slide. But this is what we need to define. So this is going to be the goal of today, to see how can we do everything in the psi eta space to interpolate functions and gradients of shape functions. All right, so if you go to the book, they do this in, I guess, in chapter 7. I want to skip this one because it's a little bit of geometry, but it's not really necessary. This is how the mapping works. There's this coordinates called barycentric coordinates, which is basically if you put any point inside of the triangle, then that point divides the triangle into 3 triangles with different area. And then basically how much influence should a point have depends on the area of these subtriangles. But this just to let you know where it comes from, but no need to know the details of this. The important part is this. So this is the important part, which is we have the XY space, and then we want to get, and we have the psi eta space. I guess in the book they do psi 1, psi 2, and we want to go from psi 1, psi 2 to XY. And so we need the shape functions, but the shape functions are going to be in terms of psi 1, psi 2. So this is super important. So no more XY shape functions. So only shape functions using these other new coordinates, psi 1 and psi 2. And so what is the first shape function? It has to be 0 at this node. Sorry, it has to be 1 at this node, but 0 at the other nodes. Any clue? They are actually super simple in this psi 1, psi 2 space. What is a function of psi 1, psi 2 that is 0 at the two nodes on the left, but 1 at the node on the right? Wild guess. Yep, just psi 1. So they just look so much simpler. In yeah, psi 1 is just 0 at the nodes on the left, but 1 at the other node. So that is your shape function. How about N2 then? N2 has to be 0 at the bottom, but 1 at the top. Psi 2. And my size is high. Tell you. And then what about N3? N3 has to be, I already gave you the equation of the line. N3 has to be 1 at the corner, but 0 at the other corner, at the other two nodes. Yeah. Yep. 1 minus psi 1 minus psi 2. So these are the shape functions in terms of psi 1, psi 2. So now no more shape functions in terms of xy. We're gonna only use shape functions in terms of psi 1, psi 2. And similar to before, now we are gonna use the shape functions twice, one to interpolate x and another to interpolate theta. So here, this node has some x1, y1, which I'm gonna call x1 vector. This one has x2, y2, which I'm gonna call x2 vector. And this one has x3 and y3, which I'm gonna call x3 vector. And additionally, we might have some nodal values in addition to these x coordinates. We might have the values of the temperature. So theta 1, theta 2, and theta 3. So what the isoparametric map tells us is that if we want to know, let's say, the value of the temperature at some location here, what we need is we can no longer evaluate shape functions directly in terms of x, y. What we're gonna have to do is evaluate both the x and the theta using our shape functions with respect to psi. Actually, let me put the dependence explicitly. So x is explicitly a function of psi1 and psi2. Theta is explicitly a function of psi1 and psi2. So if I want to plot theta as a function of x, so to plot theta as a function of x, I cannot do that explicitly. Rather, I need to evaluate both x as a function of psi, let me call it psi vector, and theta as a function of psi. So let me show you how that would look like in the code. Let me leave it more or less there. So again, we have some triangle which has some x1, y1, x2, y2, x3, y3, and some values of theta, theta1, theta2, theta3. And we have our parent triangle, which is always this one, where this is 1, 2, and 3. This one always has coordinates 1, 0, always has coordinates 0, 1, and always has coordinates 0, 0. So what this isoparametric map tells us is that what you would have to do is you would have to pick values here. Let's say that you pick the value psi1 equals 0.5, psi2 equals 0.2. Just a random number that is inside of the triangle. Then I need to evaluate both x at that value of psi1, psi2, is the sum of the shape functions evaluated at that psi1.5, psi2.2 times the nodal values. So in this case, the value of the first shape function is just psi1, so 0.5, times the value of the first coordinate, x1, plus the value of the second shape function, but the second shape function is just psi2, so this is just 0.2, evaluated at x2, plus 1 minus 0.5 minus 0.2 at x3. So that will give us some x that would be, somewhere in the middle. I don't know exactly where, but somewhere in the middle of that triangle. But again, we picked this point. So we picked Xi1 equals 0.5, Xi2 equals 0.2, and then we evaluate the corresponding xy by evaluating this map. It will tell us where that point goes to. It is really basically a map from here to here. And then we are evaluating not only that, but we're evaluating the theta. And that one is the same. So 0.5 times value of theta 1 plus 0.2 times the value of theta 2 plus 1 minus 0.5 minus 0.2 times the value of theta 3. And that will give us some value of theta that, I don't know, it will correspond to some color. And so if you want to get the contour plot, there's no way of evaluating theta directly as a function of x. What you would have to do is evaluate at many points here. So you would evaluate at many points here and just evaluate both the x map and the theta map. And then what you would end up with is you're going to end up putting a lot of color in your triangle here. Something like that. And then similarly, so this will be, let me just make it match. Obviously, the nodes are kind of matching in that so obviously the corner right there that is at 0, 0, and by whatever values you evaluate for theta at that value correspond to near the corresponding node 3 in the XY space. So that's essentially what we're going to do now. Is always evaluate this isoparametric map. Questions about that? Okay, so that one is the easy part, and then the tricky part is the derivatives, because in addition to wanting to interpolate x and theta, I also want to interpolate gradient of theta, right? So evaluating x and theta easy. So what about gradient of theta with respect to x? So what I would like is I want to compute d theta dx, d theta dy. Right? So in this case, that gradient looks something like this, right? So for this point, the gradient will look something like this. I want to know that vector. And now we have a problem. Because, like I said before, now I don't have the shape functions in terms of xy. So I don't have an explicit representation of theta as a function of x. I only have an explicit representation of theta as a function of the xi1, xi2. So I can easily get this gradient. Because that I have theta as a function of xi1, xi2. What is the gradient of theta with respect to these psi coordinates? Well, it's just the sum of the derivative of the xi with respect to xi1, theta I, the sum of the derivative of the shape functions with respect to xi2, theta 2, sorry, theta I, I can expand this out even more because the first shape function is just psi1. So actually, the derivative of the first shape function with respect to psi1 is just 1 times theta1 plus the second shape function is psi2. So the derivative with respect to psi1 is just 0. And then the third shape function is 1 minus psi1 minus psi2. So the derivative with respect to psi1 is just minus 1. So for example, that first line right there ends up being just theta1 minus theta3. Whereas for the derivative with respect to psi2, I get 0 times theta1 plus 1 times theta2 minus 1 times theta3. So the second one is just theta2 minus theta3. So actually the gradient of theta with respect to psi, that one's super easy to get, but that's not what I want. What I want is the gradient with respect to x. So how do I get that? What extra information do I have? Any ideas? Any wild ideas? It is in the next slide, but. So the other thing that we have is that x, right? So we can also take derivatives of x, so we can do, which is gonna be our Jacobian. Now this is different from the Jacobian that we did in 1D. The Jacobian in 1D was just dx d psi, or x and psi were just numbers. Now is dx with respect to the psi, this is gonna be a matrix. So this is the Jacobian. So there's going to be a matrix, which is in the next slide. Because I need to now get, it's basically, just put. Forget about this. What is the Jacobian? The Jacobian is the derivative of x with respect to psi, but now I have x and y. So I can take the derivative of x with respect to psi1, derivative of y with respect to psi1, derivative of x with respect to psi2, derivative of y with respect to psi2. Each one of these is just sum of partial derivatives with respect to either xi1 or xi2 times either xi or yi. So in particular for the triangle, we can write it out because the first one, this one is just the sum of the partial derivatives of the shape functions with respect to xi1. These are just 1, 0, minus 1 times the nodal values. So this one is going to be the same, basically, it's going to have the same structure as this, right? So this one is just x1 minus x3 of the element. This one is going to be y1 minus y3. This one is just x2 minus x3. And this one is just y2 minus y3. Because again, we have the shape functions in terms of psi1, psi2, just take derivatives and then just sum with the nodal values. All right, so we have, and let me just remind you that this is dx, psi. So again, we have two different type derivatives. At the end, I still haven't calculated this. At the end, I want the derivative of theta with respect to x. So I'm gonna get there in just 1 sec. What I have now is I have the derivative of theta with respect to psi, and I have the derivative of x with respect to psi, which is the Jacobian. And so if what I want to get is, ignore the integration part. We'll do integration next, probably after spring break. But now I want the derivative of theta with respect to x. What I'm gonna do is I'm gonna do basically chain rule. So I wanna do d theta d psi, and then d psi d x. This d theta d psi I have, this is just theta 1 minus theta 3, and then theta 2 minus theta 3. So that one I have. And then d psi dx, I don't quite have that, right? I have the x d psi, right? Well, this is just the inverse of that. So this is just the inverse. So what I'll need to do is I will multiply the inverse of that Jacobian matrix times that gradient of theta with respect to psi. So again, given a value of psi1, psi2, I can evaluate x, I can evaluate theta, I can evaluate the gradient of theta with respect to psi, I can evaluate the Jacobian, and then I need to invert the Jacobian, and then the multiplication of that inverse of that Jacobian matrix times the gradient with respect to psi will give me the gradient with respect to x, which is what I want. Again, this is because I don't have an explicit, I don't have this anymore. That's the only, I guess, downside of switching from the shape functions in terms of xy to having just everything with the parent domain, is that now we only have shape functions with psi. So then we have to do everything with those functions and derivatives with respect to those functions. So when we want the gradient with respect to xy, then we need to calculate these two parts, the inverse of the Jacobian and then the gradient with respect to psi. Yes. More?
Like the part where
the gradient of theta with respect to psi, that one is just sum of derivatives of the shape functions with respect to xy, xy2, which are super simple because the shape functions are xy1, xy2, and 1 minus xy1, xy2. So for example, the derivative of n1 with respect to xy1 is just 1. The derivative of n1 with respect to xy2 is 0. The other one is also 0 or 1, and the other one is -1 and -1. So those derivatives are very simple. And so here, the gradient of theta with respect to psi is just for the first, it's a vector, right? Because now I have psi1, psi2. The derivative with respect to psi1 is just the sum of the partials of the shape functions with respect to psi1 times the nodal values. So just, that's how I got the theta1 minus theta3. And for the second one, it's just the sum of the partial of the shape functions with respect to psi2, which is just 0, 1, minus 1. That's how I got the theta2 minus theta3. But again, this one right here is the gradient of theta with respect to psi. Which is not what I want. As we'll see when next, after spring break, we'll go back to the weak form. The weak form does not have a gradient with respect to psi. The weak form has a gradient with respect to x. So we somehow still need to be able to calculate those gradients. That's it. All right. We'll see you on Wednesday, and good luck with the homework. Hopefully you're almost done.